Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5 of flow of water through soils. In the previous lecture, we have learnt in detail about factors affecting permeability of soils. In this lecture, we will be looking into flow of water through stratified soil deposits, and we also look into the theoretical aspects in deriving or in computing seepage problems, particularly by using Laplace equation of continuity. So, the review, like the previous classes, we have started fluid flow through soils, and then we have also discussed methods for determining the coefficient of permeability of soils. Then we said that the two methods, one is constant head permeameter test, other one is falling head permeameter test, which are there in the laboratory, and we discussed the methods and merits and demerits of each methods and their suitability to a particular type of soils. In this lecture, as informed earlier, we will be looking after permeability of stratified soils and equation of continuity. So, if you recall the list of the factors affecting permeability, we have listed around 7 factors. They can be recollected. We said that shape and size of all particles, which is also an influencing factor, and void ratio, and K increases with increase in void ratio. Degree of saturation, that also we said that K increases with an increase in the degree of saturation. Composition of soil particles, we said that the mineralogy also plays a great role in influencing the coefficient of permeability for fine grained soils. Soil structure, that is whether it has flocculent structure or dispersed structure, the effect of soil structure also we have discussed. Then viscosity of the permeant, density and concentration of the permeants are the other factors affecting the coefficient of permeability. Based on these permeability values which are computed, the soil can be classified. This classification of soils according to their coefficient of permeability can be carried out as follows. In this table, if you look, the first column tells about soil type, and second column gives coefficient of permeability in meter per second, and third column gives relative permeability. So, if the soil is of coarse gravel or jointed rock, then it can have permeability greater than 10 to the power of minus 3 meter per second, and it is said that it is having high permeability. Sand, which is fine sand, it can have permeability of the order of 10 to the power of minus 3 to 10 to the power of minus 5 meter per second. It is said that of the relatively of medium permeability. Silty sand with the dirty sand with the mixed matter with organic constituents, we can say that the permeability is of the order of 10 to the power of minus 5 to 10 to the power of minus 7. We say that low permeability. Silt and a fine sandstone can have permeability in the range of 10 to the power of minus 7 to 10 to the power of minus 9 meter per second. We can say that very low permeability. When it comes to some clay and mudstone without joints, can also exhibit a permeability less than 10 to the power of minus 9 meter per second also. Then in that case, by all practical means, we will say that the soil is practically impervious. So, this particularly this classification is important in deciding say for construction of some earthen barriers or a water barriers or a compacted clay barriers for arresting the flow of contaminants from one zone to other zone. This can be taken up by using this important property of clay. So, let us look into how to arrive at the effective coefficient of permeability of stratified soils. So, as we said, in general natural soil deposits are highly stratified. We have got in the beginning of this soil mechanics lectures, we have seen that the soil deposits during the process can have layers of soils. An example can be like a warwood clay, it can have silt and clay deposits. So, in general natural soil deposits are all stratified. So, if you look into it, here in this particular figure there are some 4 layers of soils have been shown. Here a particular soil in this layer 1 is said to be a sand of certain type, and layer 2 is sand of certain type, and layer 3 is clay, and layer 4 is also another clay of another type. So, if this stratification is there and if this stratification is continuous, then our primary importance, primary goal is to how to arrive at the coefficient of permeability of the soils if they are stratified. So, if the stratification is continuous and effective coefficient of the permeabilities both in horizontal direction and vertical directions can be computed by using the fundamental principles of flow of water through soils. So, let us now consider first of all to find out coefficient of permeability of equivalent coefficient of permeability if the flow is occurring in the horizontal direction, that is parallel to the direction of stratification. So, flow in the horizontal direction, it means this that flow in the horizontal direction, that is parallel to layers. Let us assume that we have got a permeameter in which n number of layers which are having permeabilities, coefficient of permeabilities K1, K2, K3, K4 to Kn are placed horizontally at thicknesses H1, H2 to Hn. Now, if the length of the flow which is allowed in the permeameter is say L, so K1, K2, K3, K4 to Kn are the coefficient of permeabilities of stratified layers of thickness H1, H2, H3, H4 and Hn. And here if we assume that the flow is taking place from this point to this point through a head loss HL over a length L. So, in this case what is happening is that though we have got n layers, that flow entering the soil layer is Q, which is divided into Q1, Q2, Q3, Q4 to Qn. Q1 is the rate of flow passing through the first layer, and Q2 is the rate of flow occurring through the second layer, and Qn is the rate of flow occurring through that nth layer. So, this is the Q which is entering the soil mass, that is stratified soil mass, and this is the Q which is coming out of the soil mass. So, Q is equal to Q1 plus Q2 plus Q3 so on to Qn. So, condition 1 here is that Q is equal to Q1 plus Q2 plus Q3 so on to Qn, and head loss is uniformly constant. That means that all layers will have the same head loss, because horizontally though the layers are stratified, the same head which is driving the flow from point to left side to the right hand side. So, let us look into how this flow in the horizontal direction and parallel to layers can be obtained. So, for horizontal flow, here it is said the head drop HL over the same flow path length L will be the same for each layer. So, if the head loss is same, then we can say that I1, that is the hydraulic head drop which occurred in the first layer, and hydraulic gradient which occurred in the first layer, and hydraulic gradient which occurred in the second layer, and hydraulic gradient which occurred in the last layer, that is the nth layer, can be same. So, a condition is that I1 is equal to I3 is equal to I4 is equal to In. So, the flow rate through a layered block of soil of breadth B. So, assume that this permeameter has got a breadth of B perpendicular to the plane of the figure. So, in this case, by using again the Darcy's law, we can write flow rate, which is KH is on the left hand side, that will show is the coefficient of permeability of all the layers in horizontal direction, that is the equivalent coefficient of permeability, in the horizontal direction KH, and I is the hydraulic gradient, which is nothing but in this case HL by L, and B is the width perpendicular to the plane of this figure which is shown in this slide. H is the total thickness of these layers. That means that suppose if you have got 4 stratified layers, then we will have H is equal to H1 plus H2 plus H3 plus H4, or in case of n number of layers, the stratified thickness will be H is total thickness of all the layers, H is equal to H1 plus H2 plus H3 plus H4 to Hn. So, similarly, writing for the layer 1, layer 2, layer 3 to the layer n, we can write K1 I1 BH1 plus K2 I2 BH2 plus K3 I3 BH3 to Kn In BHn. So, K suffix H, that is equivalent coefficient of permeability in the horizontal direction, equal to K1 H1 plus K2 H2 plus K3 H3 so on to Kn H1 divided by H1 to Hn. So, the summation of thickness, that is the thickness of the layers of say m number of layers, and multiplication with K, the respective coefficient of permeability of that particular layer with the thickness of the layer, is going to give the coefficient of permeability, that is equivalent coefficient of permeability of all the layers under consideration in the horizontal direction, that is in the direction of the flow. So, here when we have got number of layers, say when the flow is occurring under a confined medium, say in the case, then what will happen is that the flow occurs parallel to the it should be confined in both top and bottom, and then in that case the flow will occur with a head loss at a starting point, say left point 1 to point on the right hand side to 2. So, flow will occur from 1 to 2 with some certain head Hn. So, here we said that when this particularly when the flow conditions which are occurring parallel to the layers, then we said that one condition Q is equal to Q1 plus Q2 plus Q3 is equal to Qn. Then another one we said that I1 is equal to I2 is equal to I3 is equal to In. So, with that we try to again use the coefficient of permeability and hydraulic gradient and superficial velocity relationship, V is equal to Ki, and then which is also can be extended to write a flow rate is equal to Kia, where A is the flow over which this is occurring, say A is the area over which the flow is occurring. Say if for the thickness of thickness of H1 having a width B perpendicular to its plane, then H1B is the area over which the flow is occurring. So, we have written K1I H1B. So, that is what we are seeing here. So, by simplifying we will be able to get this. So, this is the expression we have derived for equivalent coefficient of permeability in the horizontal direction, that is in the direction of the flow. Similarly, let us assume that we have got similar stratification K1, K2, K3, K4 to Kn, but the flow is occurring in the vertical direction. So, in this case it is can be said that because of some artesian pressures at the bottom, the flow is occurring in the vertical direction in the upward flow direction. So, the head loss which is driving the flow is HL, that is HL is the head drop. So, flow in the vertical direction perpendicular to layers, that means that the flow is occurring in this direction. So, K1, K2, K3 to Kn are the number of layers which are placed in this permeameter, and H is the thickness of all the layers under consideration here. Here H is equal to H1 plus H2 plus H3 so on to Hn, and here when the flow is occurring, so entire flow which is taking place here, instead of getting divided into Q1, Q2, Q3, Q4, and in the previous case we express as a summation, here it will be Q is equal to Q1 is equal to Q2 is equal to Q3 is equal to Qn. So, this is a condition 1 here, where what will happen is that Q is equal to Q1 is equal to Q3 is equal to Qn, it turns out to be one condition, because the same water is entering and then erupting out once the head is elapsed. So, when this particular condition arises for for a vertical flow, the flow rate Q through area A. So, the flow is occurring in the vertical direction, say upward direction. So, the area over which the flow is occurring, say A, and for each layers being the same. So, the head drop occurs over a series. So, this head drop across a series of layers can be said as HL is equal to head loss in first layer, head loss in second layer, head loss in third layer. Total head loss, if we can say that, that is equivalent to total head loss occurred in in all the layers. So, it can be, need not be the same for all the layers, depending upon the type of soil, then different head losses can occur. Suppose if it is a sand layer is there in that stratified and the flow is occurring in vertical direction, then you can have a certain type of head loss. If it is a clay layer is there, then it can have a certain type of head loss. So, but condition here is that for vertical flow, the flow rate through Q through an area A of each layer is same. That is what one condition, first condition we have set. The second condition is hence the head drop across a series of layers, because that is happening. So, with that the head loss which is occurring is the series can be written as HL is equal to HL1 plus HL2 plus HL3 so on to HLN. So, that can be simplified by using HL can be written as I divided by I in terms of H. The H is the total thickness of the layers, and I1 is the say head loss occurred in the first layer, then H1 is the thickness of that particular layer, then H head loss occurred in the first layer can be written as I1 times H1, where I1 is the hydraulic gradient in first layer and H1 is the thickness of the first layer under consideration. Similarly, we can write now IH is equal to I1 H1 plus I2 H2 so on to I3 H3 to IN HN. So, by writing now by using Darcy's law, V is equal to K I. So, that can be expressed as I is equal to V by K. Then by writing now V by KVH. So, where KV is the equivalent coefficient of permeability in the vertical direction. So, this is represents the equivalent coefficient of permeability for all the layers under consideration. So, V by KV, where V is the superficial velocity, being the flow is same. So, what will happen is that it will have the same velocity, V is equal to V1 is equal to V3 is equal to Vn. So, V by KVH is equal to V by K1 into H1, V by K2 into H2, V by K3 into H3 so on to V by Kn into Hn. So, by simplifying this, what we will get is KV is equal to H1 plus H2 so on to Hn divided by H1 by K1 plus H2 by K2 to so on to Hn by Kn. So, here what we can get is summation, their equivalent coefficient of permeability in the vertical direction, Kv is equal to summation of all the thickness of layers which is undergo where the vertical flow is occurring to that is summation from m is equal to 1 to n by Hm by Kvm. So, Kvm is the vertical permeability of that particular layer. For example, if is m is equal to 1, then it will happen to the first layer. If m happens to be the nth layer, then it happens to be for the nth layer. So, you can see now we have tried to determine the equivalent coefficient of permeabilities for stratified layers, and we tried to use again the fundamentals whatever we have discussed in deliberating this discussion. Now, main points which are stratified soils which are looked into be consideration are main points about stratified soils. If you summarize, in general for stratified soils KH is not equivalent to KV. KH is not equivalent to KV, that is equivalent coefficient of permeability in horizontal direction not equivalent to coefficient of permeability in vertical direction, or horizontal permeability is not equivalent to vertical permeability. As we all know, in the case of vertical permeability there is say geostatic stress, or because of the its own self-weight, soil tend to have increase in vertical stress with depth. So, with that the number of the voids which are available for the flow to take place will keep on decreasing. In a way, what will happen here in this case is that in horizontal direction, if you look into it, the scenario is different, because the horizontal stresses, that is depending upon the soil that is history, stress history of a soil, we can have different conditions of particularly for certain type of soils where this coefficient of say earth pressure rest is say less than 1. In that case, what we can have is that sigma h is horizontal stress, that is horizontal geostatic stress is less than vertical stress. Because of that reason, generally what will happen is that kh is said to be more than kv, that is coefficient of permeability in the horizontal direction is more than coefficient of vertical direction. So, if this particular condition like kh is not equivalent to kv is said, so such type of soil deposits are said to be anisotropic soils. That particularly from the flow point of view, if the permeability is not identical in both the direction consideration, then we can say that is anisotropic in condition. For example, if you are considering a flow in 3 directions, say permeability in x direction, y direction and z direction. If the permeability is not same in all the directions, say kx is not equal to ky is not equal to kz, then we will say that it is an anisotropic condition. So, here in case where soil deposit permeabilities are not the same in all directions, we say that the properties are anisotropic. If the properties are the same in all direction, then it is said that isotropic from permeability point of view. So, in this case from isotropic from the permeability point of view. As I said, because of the variation of the geostatic stresses, as sigma h is less than sigma v, we can say that generally it is observed that kh is greater than kv. The reason there can be attributed to, one is that sigma h less than sigma v. The other one in a more detailed way we can say the more voids or pore spaces are available in horizontal plane under consideration for the flow to takes place. Because of these reasons, we can say that we can explain that kh is reasons for that coefficient of permeability, higher permeability in horizontal direction than vertical direction. So, we have discussed about the stratified soils and then how the equivalent permeability can be computed, and we also said that this generally for stratified soils kh is not equivalent to kv, but it is observed that kh is greater than kv. The reasons we have explained through the geostatic stress principles. So, let us now try to look into an example where the flow is occurring in say in the horizontal direction. So, in this slide a steady flow parallel to soil layers example was considered. Here you see there are three types of soil layers which are placed in between two impermeable layers. One is one impermeable layer at the top, one impermeable layer at the bottom. So, if these conditions are there, the flow occurs parallel to parallel to this stratification. So, here there are three types of sands. One is coarse sand which is having a permeability k 10 to the power of minus 4 meter per second, and the medium sand k is equal to 0.5 into 10 to the power of minus 4 meter per second, and a coarse sand k is equal to 2 into 10 to the power of minus 4 meter per second. So, here you will see that water it has got a head of water which is 10 meters above this particular level is 10 meters, and from at a distance of 100 meters from here the head which is available is around 6 meters. That means that the head loss is occurring from point A to point B. But if you look into the head which is available at C, so this is that head which is available which is at this particular point. So, now if you look into this particular thickness of the layers, this is the top layer which is having say H1 is equal to 6 meters, H2 is equal to 4 meters, H3 is equal to 3 meters, and consider this particular bottom surface of the impermeable layer as a datum. If you consider now the flow which is taking place from point A to point B, so that is with a head of around 4 meters, this particular flow is occurring. What we are interested in estimating the equivalent coefficient of permeability in horizontal direction. So, that is the direction is equivalent to that flow of water through layers. So, here the flow which is occurring here Q entering here, and then Q is by conforming into the conservation of the mass, Q entering the flow is equivalent to the Q coming out of the flow out of the soil. So, here this flow can get divided into Q1, Q2, Q3. So, total flow which is occurring Q is equal to Q1 plus Q2 plus Q3 is equal to Q, which is coming out as a once the flow is taking place. So, now let us look into the solution how it runs. So, the solution for this particular problem, having selected datum at bottom impermeable layer, now compute total head at A, that is which is nothing but if you look into the previous slide once again, which is this 7 meters plus 13 meters is the total thickness of this layer. So, if you look into this total head which is there is elevation head plus pressure head which is around 23 meters, and total head at B which is again it's said here at 1.5 meters from this is the elevation head, and then the rest which is available is the pressure head. So, we can say here the pressure head total head available at B is 19 meters. So, head loss between A and B is difference between head A and head B, that is nothing but 23 minus 19, 4 meters. Hydraulic gradient now we can express because the horizontal length over which this flow is occurring is around 100 meters. So, hydraulic gradient is now 4 by 100 is 0.04. So, using the expression whatever we have derived that is equivalent coefficient of permeability in the horizontal direction is equal to K1 H1 plus K2 H2 plus K3 H3 divided by H1 plus H2 plus H3, because here now we are having 3 layers under consideration. So, we limited that n is equal to 3. So, by simplification, total flow is equal to sum of the flows in the layers. So, total flow can be obtained by again conforming to Darcy's law. K is equal to Q is equal to KIA. So, you know the K1 and you know I and then you know the A1. So, with that you will be able to calculate the sum of the flow in all the layers which is occurring in the 3 layers. Then equivalent coefficient of permeability can be determined as 1.077 into 10 to the power minus 4 meter per second. So, this is how the solution has to be worked out for the case of a stratified soil having 3 different type of soils. So, what we try to get is that equivalent coefficient of permeability for the all the 3 soils put 3 sand layers given in the problem put together. Now, before introducing the equation of continuity and the theory behind this and then solution which is available for equation of continuity, let us try to look into different types of fluid flows which are possible in soils. If you look into it, basically they are divided like 1-dimensional flow, 2-dimensional flow and some 3-dimensional flows and some spherical flows, but most prominent what we discussed till now, they are all 1-dimensional flows. A 1-dimensional flow condition is the one where the velocity vectors are parallel and equal in magnitude. So, in this case, say the flow is occurring with a head loss here, so from point 1 to point 2. So, this is the flow direction where the flow is taking place. A 1-dimensional flow condition is the one where the velocity vectors are all parallel and of equal in magnitude. In other words, the water always moves parallel to some axis and through a constant cross section area. In other words, water always moves parallel to the some axis through a constant cross section area. So, this is said to be in 1-dimensional flow. Steady downward flow occurs when water is pumped from an underground aquifer. So, if the water is being pumped from an underground aquifer, then there will be a pressure drop there. Then what will happen is that water flow can take place in the downward direction. Steady upward flow can occur if there is say a location of a sand layer and which is receiving a source of water from some because of the artesian conditions. So, what will happen is that if the above the sand layer, if suppose a relatively impermeable soil is there, then the water can flow through that particular soil because of the artesian pressure. So, steady upward flow occurs as a result of artesian pressure when a less permeable layer, that is the reason why I have been told that if there is a less permeable layer is underlined by a permeable layer which is connected through the ground to water source, providing the pressures higher than the local hydrostatic pressures. So, these pressures which are driving the flow in upward direction, they are receiving these higher pressures because of some artesian conditions, natural conditions which are possible. We have discussed also different aquifer conditions which are possible. So, steady upward flow occurs as a result of artesian pressure when a less permeable layer is underlined by a permeable layer which is connected through the ground to water source, providing the pressures higher than the hydrostatic pressure. So, the flow can be 1-dimensional. So, in this slide basically we have seen a 1-dimensional flow which can be occurred due to flow from point 1 to point 2 because of the head loss occurring over that particular zone. So, here in that word, in other words, we can say that the water always moves parallel to the some axis through a constant cross section area. So, this is an example for 1-dimensional flow. Another example is that flow through a confined aquifer. Suppose if you have got a flow which is occurring through a confined aquifer having say constant area of cross section, then we can say that again the flow is 1-dimensional. So, here in this slide, in this particular picture here, what you are seeing, the flow which is occurring through 2 impermeable layers and the flow is occurring through a sand layer. So, this can be said as again a 1-dimensional flow, not necessarily vertical direction. It can be because of any confined aquifer condition which is prevailing and which can also have a 1-dimensional flow. Now, the another type of the flow what we said is around 2-dimensional flow. Basically, it can occur like it occurs when all the velocity vectors are confined to a single plane, but vary in direction and magnitude within that plane. So, here a flow which is adjacent to a sheet pile wall. Generally, we keep these sheet pile walls to retain water in other end, and so in this case water flow occurs from higher head to lower head. So, higher head if you call it as upstream head and lower head is called as I say downstream head. The flow occurs from the upstream end to downstream end. So, here the yellow color member is designated as sheet pile wall, and if it is placed in a sand layer, a saturated sand layer, then we can say that this is the head which is driving the flow. So, the flow occurs from this point to this point. So, here the type pattern of the flow which is generally changes in two directions, that is x direction and z direction. That means that if you call x plane this one and z plane, then we can say this type of particular flows are called two dimensional flows, where in the z direction almost the flow Vz or the flow occurring in the z direction is almost 0. So, in that case this particular type of flows are called a two dimensional flows. So, it occurs when all the velocity vectors are confined to a single plane, but vary in the direction and magnitude within that plane. Here consider an example where the long excavation for a canal excavation is being carried out. So, here in this case the flow takes place at a particular cross section if you cut. So, here the flow is occurring in this direction. So, perpendicular to this plane, suppose if this axis is said to be say z axis along the length of the canal or length of the excavation. So, there the flow which is occurring in that direction is very minimal. So, in this also can be said as an example for a two dimensional flow conditions. So, what we are doing is that we are discussing about the different types of fluid flows in soils, and we are also trying to understand with some salient examples. In a three dimensional flow is the most general flow condition which can be said as a flow of water towards a water well. Flow of water towards a water well can be said as an example for the three dimensional flow, where you can see a borehole where the water is which was driven into the ground. You can say that the flow which is occurring all directions from spherically and which is coordinating or converging towards the center of the that is borehole can be said as an example for flow towards a water well, which is designated as a three dimensional flow. So, as we have seen and then we understood that the multi-dimensional fluid flow is possible in soils. So, as of now we said that the flow which is occurring in one direction. So, it is not the case where we can have two dimensional flows or three dimensional flows, but most of the geotechnical structures the two dimensional flow or two dimensional flows are very common. So, in the case actually our analysis and then further we are looking into the details in the two dimensional flow conditions for calculating the flow of water through an earth dam or flow or leakages in a seepage reservoir or leakages in a reservoir or so. All these things for a two dimensional flow conditions. So, as of now we have considered one dimensional flow in soils. As of now we have considered one dimensional flow in soils where all fluid is flowing in the same direction. So, in most cases however fluid in different regions will be flowing in different directions. So, if the fluid in different directions flowing in different directions, then we can say that is a multi-directional flow or multi-dimensional flow. Hence, it is required to learn how to solve the multi-dimensional flows. So, we have to develop a knowledge now how to solve these multi-dimensional flow problems in soils. So, to develop these capabilities we use the equation of continuity, this is based on the conservation of the mass, and the multidimensional forms of Darcy's law. So, again we will be using the multidimensional forms of Darcy's law and equation of continuity. With the help of these things we will try to arrive at the equation of the continuity and then the solution, and then we can application of this yielding to we can lead to evolve at calculating the seepage problems involved in earth dams or sheet pile walls. So, here an example which can elucidate this multidimensional flows is shown here, where you have got two sheet pile walls which are placed here. So, possible that the flow can occur from this upstream end to this. So, this is a where a coffer dam type, where this particular situation has been created to facilitate construction. This is generally done for pier constructions within the river bed or so. Then in that case here this coffer dams are constructed which are nothing but either spherical or having a particular shape depending upon the requirement, and the main impetus is to keep the water away. So, for that but water has always got a tendency to flow from higher head to lower head. So, in the problem here what the flow pattern which can occur is something like this, where the flow which is occurring in this direction. So, when the flow is taking place in this direction, the head loss is also occurring from the starting point to the ending point here. Similarly, the symmetry which is shown here. So, coming to the C page and equation of continuity. In many practical cases, the nature of the flow through soil is such that velocity and gradient are gradient vary throughout the medium. So, what we said is that in many practical cases, the velocity, the nature of the flow through soil is such that velocity and the gradient vary with the time and the medium. So, for these problems, calculation of flow is generally made by use of the graphical procedure called flow net methods. So, this flow net methods is nothing but the solution of the equation of continuity which we are going to derive very shortly. So, the concept of flow net is based on the Laplace equation of continuity, which describes the steady flow condition for a given point in a soil mass. So, at a given point, if this is valid for at a given point and which is occurring in a saturated soil medium. So, the concept of flow net is based on Laplace equation of continuity. So, the equation of continuity which we are going to use is named as Laplace equation of continuity, and which describes the steady flow condition for a given point in the soil mass. So, the Laplace equation of continuity describes the steady flow condition for a given point in a soil mass. Now, let us try to look into this equation of continuity, where let us assume that you have got a dam which is retained by a pier, masonry pier, which is constructed with say concrete weir or so, and which is having a head of water H1 on the upstream side, H2 on the downstream side, and it is embedded in a sandy soil or a saturated soil, and at a particular point A, just beneath the structure, suppose if you select at this particular point A, H is the head which is available there. That means that here when it is retaining, the flow is occurring from H1 to H2. So, here the head available at all these points is around H1 and H2. So, this type of problems which are possible and which are called two dimensional problems, where the problem can be, the flow can be acted in a direction here in this direction. So, where the flow can be said that Vx and Vz. Suppose if we call this is the x axis and this is the z axis, then we can say that Vx and Vz are the x and z axis over which the flow occurs. And then perpendicular to this axis, if you call it as a y, then Vy is equal to 0. For this is for a two dimensional case. But while deriving the equation of continuity, let us assume a perfectly anisotropic condition like Kx is not equivalent to Ky is not equivalent to Kz, where Kx, Ky, Kz are the coefficient of permeabilities in x direction, y direction and z direction. So, let us consider a small element at A, which is a cube which is there and which is considered with the flow which is occurring here. Let us assume that the flow at point A. The flow at point A, we can say that Qz is the flow inflow which is occurring over a plane xy plane, that is over a plane xy plane. So, let us assume that this small element which is considered element A has got dx, dy, dz directions. So, the volume of the element is dx, dy, dz, which is dx is in x direction, dy is in y direction, dz is in z direction. And qz plus dqz is the flow which is coming out. So, the net flow is around dqz. And Qx is the flow which is entered, and Qx plus dQx is the flow which has come out. Similarly, from other phase, that is xz plane, where Qy is entering and the Qz is entering and Qy is entering and Qy plus 2Qy is coming out. So, in this case what we will try to look into is that in the x direction, y direction and z direction, you have seen that Qx, the flow entering into the element and the flow coming out of the element. Now, let us try to apply these conditions and again apply the various forms of Darcy's flow and then try to derive. So, having seen at the element A, now flow entering in x direction, y direction and z direction. So, now let us consider how we can compute these flows entering the soil prism which is under consideration here, which is having dimensions dx, dy, dz. Dx is the dimension x direction, y direction and z direction. Then by using Darcy's law, we can write qx is equal to kx ix into ax, where kx is the coefficient of permeability in x direction, ix is the hydraulic gradient in the x direction, and ax is the area which is perpendicular to x direction, that is nothing but dy dz, and h is the hydraulic head at point A under consideration here. So, similarly, in case of y direction, qy is equal to ky iy ay. In case of x in the z direction, we can write kz iz az, where kz into dou h by dou z into dx by dx dy, where dou h is a small head drop which is occurring over a length here, in this case in the z direction dz. So, the dou h by dou z is representing the hydraulic gradient in z direction. So, these are the flows entering the soil prism. Similarly, now we can also write the flows leaving the soil prism, that is coming out of the particularly soil element under consideration. See here, where here mentioned here qx, qy, qz, the flows entering in x direction, y direction, z direction respectively, and kx, ky, kz are the coefficient of permeabilities in x and y and z direction, where because being our problem is that we are considering in x direction, y direction, z direction, the flow which is occurring in x direction, y direction, z direction not equal, and that means that because of the anisotropic conditions, we said that we are considering kx, ky, kz. If kx is equal to ky is equal to kz, then we can say that for isotropic case, we can say that kx is equal to ky is equal to kz is equal to k. So, the equation of the continuity can be derived based on again the flows leaving the soil prism at x, y, z directions can be written like qx plus dqx, where the dqs is the small flow change which is occurring when the flow is entering and leaving the soil prism. So, that can be written as now kx into ix plus dix, where dix is the change in the hydraulic gradient, that is can be written as now as dou square h by dou x square into over a length which is dx. So, this expression now can be simplified as kx into dou h by dou x plus dou square h by dou x square into dx, and this is occurring over area again the dy by dz. So, now qx plus dqs, similarly we can write qy plus dqy and qz plus dqz. So, now what we have got is that by using the Darcy's law, flows entering the element and flows leaving the element. Now, let us by using the principle of the conservation of the mass, let us try to derive the equation of continuity. Here, using the principle of conservation of the fluid mass, for steady flow through an incompressible medium, the assumption is that the fluid, that is medium, is incompressible. The flow entering the element is equivalent to flow leaving the element. So, which is now here q in is equal to q out. That is the principle we can say in the nutshell as the principle of the conservation of the fluid mass. For steady flow through an incompressible medium, the flow entering the element is equal to the flow leaving the element. So, from this we can write the equation of continuity by equating the flows entering the element, the sum of the flows element leaving the element entering the element in x direction, y direction, z direction can be written as qx plus qy plus qz. Similarly, the sum of the flows which are leaving the element, which is summation of qx plus dqs plus qy plus dqy plus qz plus dqz. So, by simplifying, we will get an equation by substituting the previous discussion whatever we have, and simplifying we get qx which is qx plus qy plus qz is equal to qx plus dqs plus qy plus dqy plus qz plus dqz. The simplification of that yields kx into dou square h by dou x square plus ky into dou square h by dou y square plus kz into dou square h by dou z square is equal to 0, where h is the head loss at that particular point under consideration. So, where kx, ky, kz are the coefficient of permeabilities in x, y, z direction respectively, and in this case this is a generalized expression, can also be in case of isotropic case where kx is equal to ky is equal to kz, then we can say that where kx is not equal to ky is not equal to kz is not equal to k is not equal to 0, then we can say that del square phi is equal to 0. So, that is also a condition, del square H is equal to 0 is the condition with simplified way of expressing the Laplace equation. So, the 2D flow condition in XYZ plane. So, as I said for flow through an earth dam, which is a 2-dimensional condition, or flow through a sheet pile wall structure is a again a 2-dimensional structure, or a long excavation is a 2-dimensional flow. So, for such type of flows, 2-dimensional flow in the XZ plane, we can write kx into dou square h by dou x square plus kz into dou square h by dou z square is equal to 0. So, the equation of the continuity can be simplified now with, if the soil is isotropic with respect to the permeability kx, ky, kz, and the continuity equation simplifies to because kx is equal to ky is equal to kz is equal to k in case of isotropic equation. So, in that case, as k is not equivalent to 0, coefficient of permeability cannot be equivalent to 0. In that case, we can say that dou square h by dou x square plus dou square h by dou y square plus dou square h by dou z square is equal to 0, which is the simplified Laplace's equation of continuity. Very important expression which helps in solving the some of the 2-dimensional problems for flow of water through soils. So, for 2-dimensional flow in XZ plane, if the kx is not equivalent to kz, say anisotropic as far as 2-dimensional flow is concerned, then we can say that kx into dou square h by dou x square plus kz into dou square h by dou z square is equal to 0. So, here we can say that for a dimensional flow in XZ plane, we can say that kx is not equivalent to kz. For equation of continuity, where we have seen that the flow in saturated soils where the fluid flow has uniform and constant density, the equation for conservation of fluid, this is the conservation of the fluid mass, where it is commonly called continuity equation, where dou square h by dou x square plus dou square h by dou y square plus dou square h by dou z square is equal to 0, kx is equal to ky is equal to kz is equal to k, where k is not equal to 0. So, for flow through a constant head perimeter in the laboratory, if you say that also turns out to be a 1-dimensional flow example. In such equation, the governing equation can be written as dou square h by dou z square is equal to 0. So, in this case, if the z is the depth which is here, so this particular discussion we had in the last lecture, where z is the direction over which the flow is taking place from top to bottom, then we can say that for 1-dimensional flow in the z direction, then we can say that the governing equation of continuity is dou square h by dou z square is equal to 0. So, that means that the flow in x direction, y direction is 0. So, flow is occurring only in the direction that is Vz. So, this is an example for a 1-dimensional flow condition in the laboratory constant head perimeter. The solutions which are available particularly for the Laplace equation, basically there are analytical and closed form series solutions of the partial differential equations. So, there are several solutions which are available, and these analytical and closed form solutions are quite mathematical, not very general in nature. And numerical solution methods, typically finite element or finite difference methods, they do exist and very powerful and easy to apply, can deal with heterogeneity, anisotropy, anisotropicity and 2-dimensional and 3-dimensional flow conditions. So, the solutions for this equation of continuity, what we said is that you have got analytical and closed form solutions, basically quite mathematical and then not very general. Then numerical solutions are typically based on finite element method or finite difference method, very powerful and easy to apply, can deal with heterogeneity. But the graphical techniques which are called flow net methods, which are widely used for determining the estimating the flow of water through soils in case of a 2-dimensional structures, commonly used in engineering practice to solve 2-dimensional problems. So, the flow net methods, which are the ones which can be applied for solving and computing the flow through a 2-dimensional plane, and so that you will be able to compute the seepage or leakages which are occurring in earth dams, all these things which are applied through these 2-dimensional flow conditions. So, the solutions, if we are listing out, that means we have got analytical and closed form solutions or a series of solutions of the partial differential equations, or numerical solution methods, or graphical techniques which are based on the flow net methods, which are quite common and commonly used in engineering practice to solve two-dimensional problems, flow problems of the geotechnical structures. So, this flow net methods basically they are straightforward and graphical method to solve two-dimensional seepage problems. So, flow net methods are the straightforward straightforward methods to solve two-dimensional flow problems. Solutions of Laplace equation consists of basically the flow net means is a two families of orthogonal curves in x and z direction, and these families of curves are called as a flow net. So, in this particular slide a partial flow net is shown here. The red lines which are representing the flow lines. So, these are called a flow lines and these are called some equipotential lines. So, if you see here the aspect ratio which is called is the ratio of the distance between two flow lines, that is A, and B is the distance between two equipotential lines, that is which is B. So, ratio of A to B is called aspect ratio. Generally it is the flow nets are need to be constructed by maintaining by getting it should be possible for us to insert a circle which having certain dimension, not necessarily that it should have the identical circular dimensions, but here which is the flow which is occurring in this direction. So, the space between two flow lines is called as a flow channel. The space between any two flow lines is called a flow channel, and so in this case in the partial net which is shown here, two flow channels have been shown, and here equipotential line in the sense what does it indicate is that here in the direction of the flow here, if you measure a head here, it will be same at this at each and every point on this line. So, the lines which are having equal potential, equal head, they are defined as a equipotential lines. So, the family of these equipotential lines and the flow lines, it is said to be a flow net, which is used for calculating computing or solving the seepage problems in two-dimensional case, two-dimensional problems for an application for solving the flow problems in a two-dimensional case. So, solutions to Laplace equation consists of the two families of orthogonal curves, and they are called equipotential lines or flow lines, and which is put together in network is called as a flow net. So, in this class we try to understand about the stratified soil deposits and how to determine the equivalent coefficient of permeability in the horizontal direction and the vertical direction. Then we also discussed that the reasons why we will have that coefficient of permeability in horizontal direction is more than coefficient of permeability in vertical direction. Then we try to obtain the equivalent coefficient of permeabilities in horizontal direction and vertical direction. Then we discussed that different fluid flows which are possible in soils. We said basically there are one-dimensional flows, two-dimensional flows, and then three-dimensional flows. Two-dimensional flows are the quite common basically for the constructions of the geotechnical structures where the flow occurring in two planes, that is x and z directions. Then we, based on the principles of the conservation of mass, we try to derive the equation of continuity, and that is dou square h by dou x square plus dou square h by dou x square plus dou square h by dou y square plus dou square h by dou z square is equal to 0. This is for the x and y z directions. In case of a in two-dimensional case where with an isotropic conditions, that is kx is equal to kz as far as permeability is concerned, we said that in that case the Laplace equation of continuity can be said as dou square h by dou x square plus dou square h by dou z square is equal to 0. In case of one-dimensional problems, like in the case of say constant head permeameter, the example where one-dimensional flow can occur, where we can say that if that is the flow which is occurring in the z direction, then we can say that dou square h by dou z square. So, these are the different flows which are considered, and then based on that we have considered we have derived equation of continuity. Then we have discussed the possible solutions which are available for solving the Laplace equation of continuity, and out of this we said that the flow net methods are the graphical methods which are popular for solving the two-dimensional flow problems in soils. So, in the next lecture we will be discussing more about this particular graphical technique as a solution of the Laplace equation of continuity, and we will try to see the principles of this method and try to look into the theoretical aspects as well as applications in the form of some selected problems.